All right, hello everyone, and welcome back to Zymposium, Building Better Open Source. This is our second session with Cameron Smith as our guest. Cameron Smith is a computational biologist who is working on a very interesting open source platform for experimental biology. Cameron, for the benefit of folks who are new to the show, why don't you go ahead and introduce us to the idea behind this new open source platform?
Yeah, absolutely, John. And of course, thanks again for having me back. So the big picture idea is, to take a lot of the tools that I think have been, sort of utilized to good effect, across a wide array of applications that involve both data analysis and provision of front-end user interfaces to sort of bridge the gap between people doing low-level computation and people who are doing sort of higher-level data analysis to computational biology. And so, the high-level concept is, we have an implementation of one module that does a slightly lower level task of, sort of pipelining the data analysis components. And we'd like to do two things. One is discuss, how we ought to, in the new world, as WebAssembly begins to become more widely utilized and support better tooling and have its standards solidify, how should we think about designing such a system going forward in light of these new opportunities?
Yeah, that's right. Fantastic. So in our last session, Cameron, we took a look at this project and the architecture, and you were kind enough to walk me through all of that. And I think I have a much better grasp of what's going on in this application. And we left off with homework assignments for both of us. For me, it was diving into this Python library. I'm probably going to mispronounce it, called Flight. Is that...
I believe that's correct. Yeah, Flight. It has a Y in it because the guys who got together and put it together were at Lyft initially, so it's Flyte. Yeah.
Oh, okay.
But that's the origin of the confusion in the name of the system. Yeah.
That's great. And Flight is this really interesting workflow library for Python with a special emphasis on sort of orchestrating things in the space of ML and analytics and machine learning. Does that sound about right?
Yeah. Other than, I would say they might like to mention that I think almost all of the sort of backend components sort of grew out of the Kubernetes community, and I believe are almost exclusively written in Go and interfacing with protocol buffers. But then they have one of the best interfaces in terms of a Python SDK that allows Python users who don't know anything about those sorts of things to take advantage of that technology. So, but yes,
stay out of that world. Yes, very nice.
Yes,
good attention to developer experience.
Yes.
And so I went and looked. I took a look at that, and then my other homework assignment was to basically see how PyroVelocity, which is this library that we're looking at modernizing, how this library uses Flight. And I was able to take a look at that again, and it made a lot more sense having gone through some of the documentation of Flight. So I see why you're using it. I think all that makes sense. And then your homework assignment for today was to basically put some numbers, figures, or requirements on this sort of ingest component that we've been talking about. And how did that go?
Yeah, I mean, I think it went well overall. I think the biggest issue that we have again in our field is and with the status of sort of the way that my interest in developing the sort of broader framework within which this library that I've been developing fits as an instance is that the the bounds are quite wide in terms of what might be of interest. And so, we can get into that as we discuss further. But there's, I tried to keep a sort of MVP level of parameterization in mind, to say, if we could get things supporting, this scale, the rest of the problems could be left to that particular issue, as opposed to creating a barrier to getting off the ground. And I mean that, the biggest, the most obvious sort of reason for that is simply that, I mean, there are certain projects or questions that one might like to ask that require relatively small data sets, and some of those are exemplified in the examples and the documentation of our sort of instance library that we're trying to build this framework around. But on the other hand, I mean, as many people would assume, in the genomic data space, if you talk, about multiple human genomes, for example, you can, or hundreds or thousands or tens of thousands or millions, you can easily get, up into the petabyte range. And so, or possibly beyond. And so, we don't want to stifle ourselves with sort of premature, accounting for scaling. So anyway, with those caveats, I would say, we have some general sense of what, at the front end of this system, where we want to potentially ingest fragments of this data in an on-demand setting, what some of the parameters, might look like. And, that will obviously filter through the downstream, components of the pipeline to a first approximation. And so maybe, starting there is a reasonable approach.
All right, sounds good. So just before we start diving into some of these technical details and taking a look at how we can modernize this, maybe by using some of this new stuff coming out of the WebAssembly ecosystem, I think it's worthwhile just summarizing for viewers the fact that you're trying to really target two distinct groups of users with this open source project. And one is what I might call an end user. And this end user is an experimental biologist. They maybe are not so great at coding. Maybe they can't code at all. And the end goal of this open source platform is one of these users comes in and they say, well, here's my data sources, and I want this standard data source and that standard data source and this other one, and maybe my own data that I'm going to upload or point you to. And then I want you to run these workflows on these data and show me the results when it's done. And then the other class of users, it's probably like developer biologists like yourself, who have the theory of biology, but also the theory of computer science, and can really contribute at a meaningful level to a platform like this, which is aimed at simplifying life for those end user experimental biologists. Is that right?
Yeah, that's precisely correct. And the reason for wanting to do that is to tighten the dynamics between those two sides, because and no one else in the audience who hasn't seen this happen before would have any context for it. But basically the issue has, I think many people in my field would acknowledge and agree that the issue has been that a lot of the computational biologists have ended up developing lots of libraries for themselves that ultimately do not provide a user-friendly enough terminal interface for the people who we really want to serve with these tools to be able to use. And I should say there are many organizations, entities, companies, et cetera, out there who obviously recognize certain facets of this problem. But I think even most of those would agree there are very few who have really begun to tackle it head on, and in particular in an open source context. And so, because it spans the gamut between, relatively complicated to set up infrastructure, all the way down to very complicated to perform biological experiments, there's just not been the mind share that would be required to well serve both of the connection between those two audiences. And so that's what with this platform that we're sort of preliminarily calling BioRoastery is intended to help to better bridge.
Bio Roastery. That's the name.
Bio Roastery. Yeah, well, it's a working title. At your suggestion, I went and registered some domain names last week just so that.
Good thinking.
But
just in case, and you can Google that probably. I don't think there's anything out there called that. Now you can.
Yeah.
All right, great. So, in this session, I know we talked about last week how we could basically try to figure out what these requirements, because it's an early system, you built one component, but it's a piece in a much larger picture. Basically figure out how the requirements on this component that you've built are going to shape the architecture of the bigger picture, not just in its current day sort of envisioned architecture, but also potentially as we're considering using some more modern stuff. How are those requirements going to affect the ideal architecture if it's going to be one of these sort of modernized WASM-based approaches to solving this problem? So I think that's a great recap. Hopefully all our viewers are caught up, and now we can dive into, maybe it'd be a good place to start with that architecture diagram real quick.
Yeah,
that's sort of combined.
And as I bring that up, I just want to preface that this diagram is sort of my proposal for how we would consider doing things, to the best of the technology and the sort of pre-WASM.
This would be considered like proven architecture. It's an example of an architecture that you can find architectures out there that look exactly like this. It's probably about 10 years old, which doesn't mean that's bad. 10-year-old architectures are great. They're reliable. They're relatively risk-free. People know how to build them and maintain them and whatnot. But also there could be potential benefits in, I think I mentioned last week that there are potentially ways to simplify this quite significantly using something like Golem. So we'll talk about that later. But for now, this is the architecture. And the little piece that we've done so far is in workflow execution for a particular workflow. So basically like a prototype workflow, which would be plugged into this platform. Is that right?
That's precisely correct. We have sort of a microcosm that is implemented in a manner which is relatively scalable, but hasn't had its limits pushed yet in this box. And the structure of that is a very sort of simple, workflow that you can map, in the traditional sense of that term, over multiple data sets and internally map each over multiple model training pipelines. And so this sort of nested mapping is essentially otherwise linear and parallelizable workflow system to basically train distinct models on distinct data sets is roughly what's reasonably well to the to the level of what would be expected in computational biology implemented in this block here. But there's no user interface. There is some lineage artifact lineage tracking that's incorporated, but aside from that, the ability to build, a performant front end is still awaiting other back-end components to be integrated. And part of the question is, can we leapfrog, as you suggested, the 10-year-old architecture? And how can we begin investigating where we might consider doing experiments with leapfrogging? Yeah,
that's right. Okay, and so these requirements you gathered, are they for workflow execution in general or just the platform as a whole?
Excuse me. Yeah, so the ones that I'm sort of prepared to discuss in most detail are really pertaining to and I hope people don't think this is too boring in some ways, but are pertaining to what might become a first component that we would consider abstracting actually out of
Yeah.
this sort of workflow box and saying, hey, we could start by doing a little, prototyping experiment where we
Yeah.
say, this process of ingesting and, validating hashes on and tracking, sort of data that we might ingest and that might then serve as the inputs for many other types of workflows, even than the sort of example we have running currently. That's we thought maybe, this is a good module from the workflow, execution engine that we've been working with to consider kind of abstracting out into something which would be like a data ingestion service, but one which could have, in the ideal case, I suppose, you would implement 2 versions of it and really battle test which one is doing well. And as boring as possibly the functionality of that is, I think if we don't start at the top, it'll be harder to be able to really, properly compare what advantages and what disadvantages are we currently facing, in the context of trying to assess when are the tools from this amazing new space going to be sort of ready for prime time. So in that sense, I think we'll probably end up maybe discussing, this almost ad nauseum relative to the interest of its functionality. But the goal, I think, is to, be able to really do something where we can look at the boundary between, sort of a traditional way of implementing things and what advantages we might get by thinking through doing something similar in WebAssembly.
Makes sense. All right. So do you want to walk me through the requirements you put together?
Yeah, absolutely. So the sort of the start of this, in the background would be that, maybe we have on the order of tens of people, working on the platform. And the idea would be, they want to, if we started sort of thinking through a sort of user story, which could actually, justify, just beginning to prototype little bits of a front end, is they want to be able to come in and provide sort of unique identifiers of data sets that are available in basically the 3 primary sort of sources of genomic data that are hosted by governmental agencies and the public. So there's this collaboration between Europe, the US, and Japan, essentially. But for the sake of this discussion, we could look at sort of as how things go with the US based system, where you end up with a unique identifier for each data set or data type that you want to ingest. And so the user is going to be able, if they may bring their own data separately, but insofar as they want to integrate their analyses or prototype their analyses, thinking through doing experimental design with existing data sets, which is commonly the case, they will come with this information. So they will say, okay, I have a list of these 3 identifiers, and I don't want to get into the weeds of possibly how poorly the system is designed to to allow
I can imagine,
people.
trust me.
Yeah, we could. I mean, we do not want to go into a 2-hour long session about that, although we unfortunately could. But as bad as it is, it does sort of work, and it's something we can work around, and it's something we're not going to change. So for our purposes, we can think of these as just a list of numbers. So I mean, it doesn't even matter. They're basically like this.
The point is, you have a way, quite complicated probably, to map from one of these identifiers to an HTTP connection that lets you download the data, something like that.
Precisely. And I mean, there are all sorts of things. They are trying to do interesting things in the sense that, there are mirrors now actually of a lot of these data sets directly from those IDs, both in S3 and GCS.
Oh,
Which is being managed, from the top here. This is NCBI, just for reference, stands for the National Center for Biotechnology Information. So this is the one I'm pulling out, the U.S. governmental agency out of these three, and the SRA stands for Sequence Read Archive, as opposed to, say, in Europe, the European Nucleotide Archive, just so that I don't stop us out with too many acronyms at the top. But the point for our purposes, as you suggested, is we can map these to an endpoint or a URI of some sort, where we can say, hey, this exists somewhere, and we would like to analyze it. And there are people out there working on tools to and some of these are even being, sort of promoted by the governmental agencies as well, to be able to try to, say, well, you've already got these, on S3. Could I just stream the data through my, pipeline and so forth? But anyway,
eventually, I'm sure that'll happen, but it'll probably take a long time.
There are things that begin to approximate it, but in my experience, they just don't quite work as we'd hope yet. So anyway, suffice it to say, for now, we frustratingly all knowing how inefficient it is, we'll make a copy of this data into our own object storage. So this is the very, very top, so the experimental people know how to find these IDs in papers and databases, and they're going to come with this, and we've got to basically have the service that will do that mapping for them.
Okay.
But that I won't get into the details of, because ultimately it just bottoms out in some URI. But then for us, then we say, okay, well, how big are these data sets going to be? And
exactly.
How frequently are we going to be ingesting them, right?
All that fun stuff.
And so the good thing about that, of course, is as efficient as it is for us to be making copies of these data. On the other hand, part of the advantage of sort of building a platform on top of good tools is that obviously, we'll use some sort of system that's functionally supporting things like content addressable storage. And so at least, these common data sets, for example, we'll pull in a background copy of the reference human genome. Well, that's only really going to be happening once, and if at all, in some cases, but that thing can be well cached, and then the sort of range of data set sizes that I want to try to account for in terms of sort of where this bottoms out in the beginning is somewhere in the neighborhood of a few gigabytes to on the order of 10 terabytes. And you can tell me if that's unrealistic. We could chop the top off a little bit, but I think given the way these things work, and I mean, obviously this is limited by things that are out of our control to an extent, but this is basically where we want to start. And given the ability to cache these data sets, and that some of them, are unique, and there aren't actually, at the very fringe of new experimental techniques, there may only be, 3 or 4 distinct data sets. So when you capture those, people might imagine there would be, maybe people are, needing to download thousands and thousands of these every day or week. But actually, I think when you sort of begin to, account for, wanting to start at the fringe of what's possible experimentally, and that these data sets are actually not that common. So if you start there, I think actually, in terms of the frequency of sort of importing novel data sets, if we think about even just 10 per week, actually would be a reasonable starting point. And so maybe that's cutting across, the wide range of data volumes that we might be interested in. But then I think we can do a really nice job of at least, caching these things and if all of these components, for example, were already connected to the object store that's provided by the governmental service, we wouldn't need to do this. But until that happens, I think that the best we can do is at least design a system as I think everyone probably who would be watching this would in such a way that makes obviously good use of caching technology. That's probably the most. That's probably as obvious as that is. That's probably the most important. In my view, feature to ensure that, and obviously in doing that, validating that you've got, the right data, and of course they provide ability to that.
Some technical questions here. 10 times a week for model sizes ranging from 1 gig to 10 terabytes. Is that per user or the total load on the system?
Yeah, that I'm hoping that at least with a bank of I should say per a given user sort of user set or user subset. So when I say maybe 10x per week, I'm thinking of a factor of 10 like per 100 users. I should say something like this. So I think that's still a good parameter, but obviously it's not absolute. So yeah, I mean, obviously if there are, but on the other hand, maybe that totally asymptotes off at like 1,000 users just because of the fact that there are only so many of these data sets sort of out there. Yeah.
So basically, there are the identifier. Uniquely identifies a data set, and the data set does not change. It's not like they're updating it all the time, right? So date range or version is not a component of these data sets, is it?
That's a good question. Essentially, we can consider these are like data set hashes. They're
immutable
versions.
Pretty much.
Okay. The governmental databases, I would say, they consider once the data are there. Actually, I don't know if there's like a formal policy about that, but as far as I know, they are essentially immutable. The only thing that's not immutable is, of course, they do have a versioning system for things like the human genome reconstruction from small reads, and so that thing, each one is immutable. But of course, there may be many. But for our purposes, we can consider these immutable, I think, and I think that's more or less correct. Yeah.
All right. So you get all these, let's say, 20 different data sources, and you download them. Each one is sized 10 gigs to 10 terabytes.
I just popped it up. Yeah.
You immediately store it in S3, and the reason for that is just so you can do the computation sort of locally, if you will, from your own storage without having to worry about connection difficulties or any other issues like that. Benefit from increased locality and so forth. And then what comes next? This ingestion process there? This is just describing how it would be done.
Yes, that's correct. The ingestion process is just meant to represent sort of functionally, given these parameters, sort of, how would someone indicate that they want to, that they're authenticated and authorized to do such a thing, and then what would proceed basically from there, sort of inputting a given list of such identifiers as the system would then proceed to respond by trying to orchestrate this ingestion procedure.
Okay, and another question here, perhaps you know the answer to it. Obviously 10 terabytes is quite a lot of data, and there's no problem downloading it, but the bigger something is, the more likely is there's some sort of connection glitch on either side. So I'm wondering if if these data sources support resumable downloads. Basically, there's a accept ranges header that you can use on HTTP connections to say, I only want the bytes from here onward. Do you know if they do?
Absolutely.
Okay.
I think I should partition. So obviously, if you choose to use the source that they already have in object storage, all of those APIs would already support, resumable downloads. I believe even the direct, HTTP and FTP connections they have set up do also support this. I've done this with a couple of different, tools like ARIA and so forth that support, on the client side utilizing these features. So with those APIs, so I'm quite, but for our purposes, we can imagine we'll restrict to actually doing an S3 or, let's say object storage to object storage, data transfer process, which they have services, obviously, that, you can manage services now, that do some of those things if you want to set that up. And, you could obviously just, put together a bit of Terraform and so forth and probably fire things off, through the cloud APIs to do some of this. But the problem with that is, I'm sort of giving this as a prototypical example. Then there's all this sort of other data that's not hosted.
Right.
So I'm giving this as the most
you want the
canonical
pluggable,
source.
extensible system here for downloading data from any number of data sources, ever expanding data sources, probably over time.
Yeah, absolutely. And so this is the other reason for the wide range. So some people might see this and think that I'm being ridiculous about the lower bound, say it's always more than that. So that the reason I'm including that, at such a low level is that most of these data sets, when you're downloading raw sequence read data, will be, maybe at least tens, if not hundreds of gigabytes, and many of them now because you've got multiple files and so forth that getting up into this range. But the problem is, I'm sort of cutting off the reality here a bit. The bigger issue, there's all these other sources with like smaller data. Some of those may be behind less reliable servers, and so we for the purposes of this discussion, I think we can largely stick to how would we deal with the big guys in terms of and they have data sets that range in this side, but just to clarify, like the reason for the lower end it being so low, and I mean initially I had it at 1 gigabyte. Maybe that's fair the more I'm thinking about it. Is that we've got all these little sources around, and so I mean that'll eventually become something that would have to be addressed. But to start with, if we had something working for these purposes, that would serve a huge swath of the use cases. So anyway, this is why
two other
this is why we can't
questions.
just use the object storage transfer service directly from the cloud provider. Is what I really wanted to get to. Sorry. Yeah,
makes sense. Yeah. So two other questions. One of them being, do you have any API rate limits for these INSDC sources?
Yes. So for these, there are, and
is that a giant number that we don't have to worry about, or is that something we're going to have to factor in?
No, because we are downloading, in the grand scheme of things, relatively, few large files. And obviously, when we start splitting them up, we would have to keep track of that. But for our purposes, we can work under the assumption that these rate limits would be unlikely to impact us. The place where they come in more into effect is, in particular, I'm thinking of with the European API. Actually, they support directly say, oh, you give me a list of genes and I will give you the entire sequence of all of those genes, from directly from our API. So that's not, that API, would have a much, that API coupled with that use case, would lead to a much more significant issue. But I think for our purposes, in terms of downloading these files, certainly, again, if we are using the object storage sources, these wouldn't be likely to come into play. I mean, unless we,
I might change your mind about that in a second.
Well, unless we tweak the parameters to be downloading, concurrently, so many small.
That's what
fragments.
I'm thinking. Is that if you have 10 terabytes,
can
we do 100 concurrent requests? each downloading a different portion of that file if we want to accelerate the progress.
Yes,
Does that even matter?
I should find out what exactly would be a good number for like the semaphore, limits, for like the, NCBI sort of SRA,
and this
FTP,
somewhat
HTTP,
comes
API.
back, I think, to obviously if you have very high API rate limits, then we can parallelize the download because of what you said about resumable downloads, accept ranges, etc. So I think that's great because you would be able to potentially get something that takes minutes or hours down to something that executes really, really fast. But I think whether or not that's viable is going to depend on the API rate limits, and also how they're enforced by the hour, by the minute, by the user, whatever. Do you need the API token? I don't know this yet. But then also it's going to be influenced by the user's expected or anticipated or required cost of hosting this infrastructure. So are they going to be able and willing to pay for low latency downloads? Or is that not relevant? I mean, you could tell me that the experimental biologist doesn't care if this thing takes 12 hours or 12 minutes, it's all the same to them. Or you could say, this is extremely important from an end user's perspective, and they're willing to pay additional money for it in the terms of expanded infrastructure in order to be able to do this analysis as fast as possible.
Yeah, absolutely. I think that, sorry, I don't have a slightly more, a slightly tighter figure here for this. But I think for the purposes of our discussion, we can say, yes, for the most part, the users are willing to let this trickle in, at a relatively slow, pace without, paying, there's not some mission critical thing where it's going to make a huge difference if this finishes, especially let's say the 10 terabyte jobs, in less than a day or 2 days or something like this. But at the same time, I'm quite certain, the API limits will allow us to parallelize the download to some extent, even if, but I don't know if the limit's like, technically 10 or 10,000. I think it's on the order of like 100 concurrents, and and it's like, they measures. There's something I've looked it up a couple of times. I don't, it's something about, it's actually a bit bizarre. I can come next time we chat with a bit more detail, but it's something like they count also something per hour and so forth. I vaguely recall. So obviously these would need to be better ironed out. But I think in the implementation, but I think for sure that we can imagine that we will be able to parallelize with some sort of semaphore limit, that's maybe on the order of like, let's say for the sake, in fact, I know I've done it before with a semaphore limit specifically of 30. So let's say, but maybe can be tweaked up or down from there. Yeah.
And then with limits of any kind comes the whole question of rationing. So you have 10 users or 100 users on the system, and basically the system has so many data sets per concurrent data set downloads, and you have to decide, is that going to the first user who's requesting 1,000 new data sets, or are you going to try to split that in some sort of fair fashion across all the users of the system? And that's going to affect the architecture, how we design for that.
Got it.
And if you don't care, if it doesn't matter, and that's another thing. I know isolating workloads in Spark clusters is something that's given people lots of headache in the past.
Right. Yeah, no, that's a good point. I think we can imagine that we basically would be working to begin with, with like one pool. And this is sort of related,
and is that true more generally? Like for all compute resources, we're basically saying there's one big pool and everyone gets some. And if everyone wants a lot, then things just get slower.
Yeah, maybe not for all. So I think for the ingestion, because there's this kind of collapse of the total number of data sets that you
Okay.
would be working on.
Yeah.
The likelihood that if we're getting up in the range where people are requesting hundreds or thousands of data sets, that we've got overlap is very high.
Yeah.
So in that sense, I think treating them as one pool makes sense in this particular component. Now,
Yes.
downstream, for things like doing smaller scale analyses, like as is already sort of implicit in the fact that these workflows get distributed to a Kubernetes cluster.
Yeah.
There's some adaptation and scalability there that's available, obviously within the limits of whatever are set on the node pools in the cluster and so forth.
Yes.
But I think, broadly speaking, for those downstream steps, we want to allow a little more elasticity. For this step, there's a lot of shared interest where having everything in one pool makes sense, because just the variety is not sufficiently large to justify, I think, sort of sharding it out into multiple distinct pools of resources. Yeah.
And you make a note here that it's important to verify the data integrity of these downloads into S3. So I'm wondering if, like, I don't know, some sort of hash is available at the time when you download.
Yes,
there is.
There are associated, I believe, there SHA-256 hashes. Okay. With that basically you can grab an association with each of these and then validate, that your download obviously has been hasn't been corrupted, which is probably super important to the extent that we push, the sort of concurrency of and reintegration of those.
Yeah. Okay. So this makes sense. So this is obviously something that we want the entire process to be reliable, in the sense that we are relying on this phase of a workflow before we can proceed to the next step. So it doesn't really matter what sort of transient errors we might encounter while we're downloading these data sets. Ultimately, the download of these data sets needs to succeed because it's blocking us from proceeding to the next step of the workflow.
Yeah. So, and sorry, continue.
Go ahead.
No, I was just saying that, the advantage that comes on that from that, perspective is just that obviously, if the user's doing this manually, they tend to use very inefficient approaches. They won't make their downloads concurrent, and that works maybe up to a couple hundred gigs. And when you get beyond that, basically there are people who like, I want to analyze this data, but I actually don't know how to download it. I have actually heard of this happening, and so the fact that they could just come to the interface, as simple as this sounds, and expect that the background system will, of course, deal with those things properly is actually an advantage over what's sort of the traditional approach, which at best would be to use a tool like ARIA 2C or something like that in most cases. Yeah.
So I'm seeing requirements for, obviously, concurrency here, because we potentially want to be doing, well, first off, there's two dimensions of concurrency. There's the fact that you have multiple users on the system who are each executing multiple downloads. But then also within any given download, we have additional concurrency because we might try to accelerate the download. So we have multiple layers of concurrency, which means we do need a solution that is highly concurrent. And we get concurrency, it seems like, from Flight that gives us some concurrency. Also, if you were to use Dapper, then you can do a lot of concurrent things with Dapper. It's designed for building distributed systems. So I see where that need for concurrency is potentially being met by this existing architecture. But I think it's worth just noting that, yes, this is a massively, well, not massively, but it is a highly concurrent system. And designing that with a high degree of concurrency in mind up front is important. Also, the reliability is important. And the reliability becomes even more important when you start to get fancy about the way you download these big data sets. Because let's say you're doing 1,000 concurrent downloads for a single data set, and chunk number 998 fails. Right? That can't fail. I mean, it can fail transiently, but obviously you want that download to succeed in the long run. And when it does, then fine, you have all your chunks and you can proceed to the next step of the process. So you have requirement here for a technical requirement for high reliability and high concurrency, and a business requirement for high reliability. Because if one failure in the middle of this workflow, such as one that could occur here when you're downloading a big file in 1,000-page chunks, could potentially halt the entire workflow, and that's not acceptable to the end user. So we've got concurrency, we've got high reliability, and we've got some very concrete numbers, I think, around the scalability. And the nice thing about these numbers is I don't see anything that's crazy or alarming. I think especially given the fact that we can parallelize these downloads, we're going to be in reasonably good shape. I think coordinating and sort of orchestrating this process of concurrent downloading in pages, if you will, does introduce some complexity. But again, part of the reason we're having this conversation is because there are newer approaches to solving some of these problems, building distributed systems like Golem, that have the promise to radically simplify that type of orchestration and coordination and give you high reliability out of the box. So for your current, the workflow that I took a look at in PyroVelocity, can we maybe take a look at code responsible for downloading? Or maybe that code is already just pulling from S3? I didn't look at that.
Yeah. So, in this case, the source data are, have been sort of cached into an S3, an object storage that we control at the beginning.
Yes.
But there is still the fact that for each execution of the workflow, this first task, which ingests the data, and this may be something we could discuss, as we talk about building even the ingestion to better support its utilization downstream in the first pre-processing or ETL type steps, is that when you initiate a flight workflow execution, depending on how you set up your interface, and this is the simplest one you can imagine, it actually it will download a full copy of the data set onto the node that's gonna then perform the pre-processing. And so, in general, now that you've got things in object storage, if you're working in the terabyte range, you're going to want to start doing something more sophisticated than that. But these particular example data sets, here on the order of tens of gigabytes, not more than 100. And so in those cases, it's, relatively straightforward to just have this sort of workflow function that we dispatch to accept sort of at the top of the workflow configuration, an object storage URI, and then that's loading it onto the node to pre-process. And
so this occurs downstream of the component we're really architecting.
Yeah, and that's why in some ways it's not crystal clear, in what we're discussing, the current workflow really doesn't address actually this problem properly yet. Yeah. And so in that sense, this is now another problem in a way, which is when you want to start doing actually operating on these data. Okay, now you've got them into an object storage location that you can control, but of course, now you ideally are not streaming 7.5 terabytes, or not streaming, you're not downloading 7.5 terabytes onto a solid state drive that's going to be, associated to this particular node in your workflow. We could talk about that later, but in some ways this is doing a very unsophisticated version because we've already sort of pre-ingested the data sets here, although it is then working with those. So I suppose download is in some ways a disingenuous name for this workflow task, because it's not downloading it.
It's the
directly
download.
from an external source. Yeah, it's downloading it for the purpose of executing the workflow.
Download locally.
And so what we're talking about is a more sophisticated, basically, component than what's currently implemented. Yeah.
And that also, just from an architectural perspective, raises the question of, well, if I'm going to download it to S3, and then later I'm going to download it from S3 to a local node, maybe I should just skip that intermediate step, or not skip it per se, but if there's some way I can do the computation in a streaming fashion, then while I'm dumping it or copying, replicating it into S3, maybe I can also be doing some compute and analysis then when I have the data in memory as I'm writing these chunks out to S3. To what extent would you rely? I know Flight has support for like fan out and fan in operators for these workflows, which allows you to, I guess, do a bunch of things concurrently and collect results. To what extent do you think you would be using that in this architecture?
Yeah, that's well, yeah, no, now that you mention it, I mean, that actually raises an interesting point, because it may well be that I suppose the way that I've drawn the architecture here, implies, that these workflows are more designed around sort of post ETL, post pre-processing sort of things, where you've already sort of whittled down these 10 terabytes into maybe tens of, or hundreds of gigabytes in terms of the pre-processing. So it may be that a better architecture would be to even, I mean, I suppose you could even ask the question of whether, if you do that, you'd even need to cache the input data. If you could basically stream the transformation process through an alternative Flight workflow, so that the total size of what you store, could be significantly smaller, and that is conceivable. But I think for our discussion, probably it makes sense to say, this would be an advantage of possibly using a slightly different approach to the kind of external to internal sort of overall ETL. It's not just about ingesting the data, but it's in a sense about transforming it into something that's more efficient to store. And so for that component, we could consider using another Flight workflow, but we could consider sort of building that in to an extent to things that might be dispatched from WebAssembly components as well. It's an interesting point that maybe we could circumvent some of the problems here. We still might ultimately stream this much data one time, but maybe after that we could then reduce the footprint.
If there's some way to do the pre-processing in a streaming fashion, then I think you could basically, think of this as a data pipeline, and data is streaming in from one side, and it's being pre-processed and is being filtered, and then maybe even it's being analyzed and is being dumped out the other side. But I think we still have to keep in mind the more general case. I don't know if you're going to run into this, but like, it's common when doing analytics and machine learning in other domains that you have data sets which need to be joined, and the joins can very seldom be done in a streaming fashion. You have to index one, and then you can do it in a streaming fashion with another one, for example. Or you might have to index both of them, or you might have to do something even more complicated in order to join them up. I'm not sure to what extent you have that problem. Maybe you do.
Yeah. I think there are a number of canonical tasks, that can operate on a single data set without any need for in doing any sort of downstream joining or incorporated joining. But there are others that would require this, probably. But those would hopefully operate on the downstream data. Let me just give an example of one application which you yourself probably, since you did some work in computational biology, would be familiar with. Is one of the steps that is most of these genomic sequencing reads are relatively short. So the first step, if you really start with the raw data from one of these read databases, is to basically take the short fragments and run it through a very standardized but somewhat expensive pipeline, to map those reads to a particular location in the genome. And then you have a data set which doesn't require you anymore, though, to store the entirety of each read. And so, like, that particular read mapping process is something which is more or less universally going to be required to apply to most of these data sets.
Yes.
And so it is possible, for example, I think that particular operation would be something we could lift. Currently, we don't do it in that example workflow, but there are many other workflows for which we would need to do that. And so we could try to lift that particular step, for example, out of the pre-processing in the sort of preparation for model training and into the data ingestion service, which would have the advantage that it would probably, it would radically reduce the total size of the object we would need to operate upon. And we could probably then, there are probably some downstream tasks where it'd be nice to be able to map back to the original source read, but there are a number of tasks you could perform where you could more or less totally ignore that. And so, I think, whether you perform that operation and then keep a copy of the reads, or just perform it and never actually make a copy of the underlying reads, could be an argument in either case to include like this particular really fundamental step with the data ingestion while you stream it, so that you never have the problem that I was beginning to realize, which is this issue of bringing multiple terabytes into a single node's drive, which isn't very practical or desirable. So I think basically maybe now, as we're getting into the details a bit more, I'm seeing that maybe the concept for a pure data ingestion service, if you took that strictly, isn't maybe the right piece in this architecture. It should be something that's doing or has the capability to do a little bit of transformation, even if you do end up keeping a copy.
And you can see that you can almost imagine that like a data loader can be split into two pieces, right? It's the upfront part, which reads data from some source, and it's the back end part, which writes that data to somewhere else, and that's the process of data loading. Well, if we take that single thing, the data loader, and split it apart, then we have sort of a way to read over here, a way to write over here, and then we can insert stuff in there, which can do pre-processing and filtering and focus on the pipeline. So it may end up being that in our new architecture, we have a more explicit concept of a pipeline, and then the pipeline maybe writes artifacts to, in some cases, you will probably need to write an artifact somewhere, and that feeds into subsequent steps in the workflow.
No, this is great. I think,
There's one more thing I wanted to ask about, and that is
go right ahead.
Replicatability. Like, so just a part of me is very cautious in assuming that every single one of these data sets is going to be immutable. Because what if a researcher comes into this platform and they execute a workflow on these data sets, they get back the final result, but we don't store any of the intermediate data sets. We don't store any of these government data sources. And so they get back this and they say, oh, wow, look what I found. Here it is. People go to replicate it. And then because these data sources have changed in maybe subtle ways, maybe not so subtle ways, it fails to replicate. And there's no way to really figure out what went wrong. So, you don't have to store the whole thing. We could store a hash or something like that to say, oh, we worked on this version. And that hash is proof that if someone else has that out there. So we don't necessarily need it, but we should at least think, if replicatability is important here, then we need to bake that in as part of this architecture in one fashion or another, hashes or copies of the data sets.
Yeah, that's interesting. Yeah, you swung me back and forth there with that idea. At first, I was thinking when you were suggesting this that, you know, we still get a lot of advantage if, for example, we execute this one or possibly a couple of transformation workloads during the ingestion as we stream it into object storage, even if we end up paying the cost of storing a copy of the data set for the purposes that you suggested, such as being able to then really guarantee that, yes, we verified that we got the correct hash from the data source.
Yes.
And we have a copy of that in case, as I said, I don't know if there's a formal policy that these are really the mapping between the identifiers and the hash at any one time are truly immutable, in the sense that they might update the underlying data set, keep the data if there's some issue with it. So probably, I think the most, I think the best outcome that's beginning to come to my mind from what we've discussed is we probably keep a copy. We keep, obviously we could rehash it, but we keep a copy of what we computed the hash to be in association with the hash that we downloaded at the time. But as opposed to not doing any transformation on the data during this ingestion process, which is what I originally had in mind, we should include a couple of these, the ability to at least to include a couple of these transformation processes, so that probably we never have to touch that, big source data directly again. But for the reasons you described, we really probably should be storing a copy. And, object storage is cheap as long as you're not shuttling it over the network all the time. So I think this kind of helps to address both of those, issues.
A side benefit is if another user does a workflow, or the same user on that same data set, if it is stored locally, presumably we can process that a lot faster.
Exactly.
So I think, initially during that ingest, we are streaming it out there for the first time, if it's not already here. But also we're doing this pre-processing on it to reduce the set of the data set, store the intermediate result, which is going to be used downstream. But then the next time someone else needs anything done with that data set, we can use our copy, which sits in S3.
Yeah, and that would be nicely, that would all nicely work out in the caching system, because basically, the parameters of that first process are very unlikely to need to be tweaked. But if someone said, hey, I really need to tweak the parameters of the, read mapping process, then we say, well, okay, we have the data, we'll have to rerun that job.
Yes.
It's a big data set. We don't want to do that very frequently, but, if we need to, we will. But most of the time, they're going to say, yeah, I'll accept the pre-cached, in this case, read mapping downstream. And now all of a sudden we've reduced our 7.5 terabyte problem to a few hundred gigs, which is much more likely, to be able to, be efficiently usable downstream. So I think that's a nice takeaway.
So
given the time.
This has been fantastically useful. I think what we did in this session is we drilled down into the exact component we're going to try to modernize, using a more sort of next generation architecture. And even more importantly than understanding that component is understanding the requirements around it. And we talked about those in terms of sort of how big these data sets are, how many users are going to be downloading them, how often they're going to be downloading these data sets, degree of overlap between them, also whether or not we can parallelize the download for these really, really large 100 terabytes data sets. We talked about all that. We talked briefly about the requirement for high reliability, and just to have this thing work, and because it's the early step in any workflow would be ingesting this data. And then furthermore, I think we figured out that it could be useful to consider some sort of streaming architecture early on to help us with the pre-processing and whittling down these data sets to a size that's going to be more viable to load onto single nodes. And we didn't talk about parallelism. Maybe we can do that a bit in the next section, but I think I have a reasonably complete understanding of the system and the requirements that in our next session we can actually build out an architecture for this, a sort of next gen architecture, and see what sorts of simplifications we can get out of that. and also make sure that we're hitting all of these requirements. So that's why the requirements are so essential, because if you went and told me different requirements, that would lead to a totally different architecture. But with these requirements, I think we'll be able to do a good job defining a shape around which, we'll know there's a little wiggle room in a few places, but roughly the requirements you've given me have dictated a lot of what we have to make in this next generation architecture. So I look forward to doing that next week with you.
Yeah, thank you so much, John. This definitely became more interesting than I thought it was going to be by
there's a lot of meat if you.
Yeah. And so I now I actually feel, maybe a little more comfortable than I initially did at saying, are we really going to, talk about data download? Like nobody. Yeah. Even though I knew as we delved into some of the details, we would get to some things that, are not obvious, as all of us, I think, who have worked in any engineering problem have gone through this sort of phase of, oh yeah, that's going to be easy.
It's easy. I'll have it done by tomorrow.
Yeah.
2 weeks later. Yes.
Absolutely, John. All right.
All right. Well, thanks,
thank you
Cameron.
so much.
See you next week.
Take care. Bye-bye.
Bye-bye.